Hi, welcome to example 8 in our functions and graphs topic, and we're talking about points of inflection in this example. You might have come across the idea of a point of inflection when you're looking at stationary points, and when you were looking at the idea of a turning point, a maximum or a minimum turning point, you'll notice there's a change in the direction of the sign of the gradient, in one case from negative to positive, and in another case from positive to negative. So in a turning point, there's a change in the sign of the gradient from positive to negative. In a point of inflection, at a stationary point, there is of course no change. It's either negative and negative on either side, or both positive, a rising or a falling point of inflection. So you might think, well, that's all points of inflections are. Well, in actual fact, there's a lot more points of inflection than you might think, because that's not actually the definition of a point of inflection. They often don't happen at a stationary point. So the gradient is not always zero at a point of inflection. So I'm going to show you a couple of images of two other points of inflection. And you'll notice, of course, the gradient's not zero at those points, but something particular does happen in all three instances. That, again, just like in our turning points, there's a change from the left to the right, and that in a turning point, that's a gradient sign, negative to positive or positive to negative. In a point of inflection, it's actually a change of concavity from what we call concave down to concave up, or the other way around. So this idea of the nature of its concavity, that's today's word, concavity. So when there's a change in concavity, we have a point of inflection. So what on earth is concave up and concave down? Because if you notice, it's slightly weird. See at this point here, concave down. The issue is it's actually, it looks like it's kind of, we've got a maximum turning point in there. It's going up and down, and concave up doesn't look like it's going up. It's not about, we think sometimes about gradient when we think about up and down, but we have to define concave in its own way. So here's my explanation of what concave up and down is. So if we have a look at this curve here, we've got we've got a maximum turning point and minimum turning point, and somewhere on this green dot we've got our point of inflection. This is concave down on the left and concave up. How on earth are we able to distinguish between the two? Well, let's have a look at their gradients. Okay, on the left hand side, if we were to take snapshots, I've put some little tangents at various points, and we can see on the left hand side it's going to be positive. So say for instance it's your gradient's 2, but then it's flattening out, so the gradient goes to 1, and at the top, of course, at the stationary point, it's 0, and then the gradient turns negative. So that would be a snapshot of the gradients of the curve there. What we can say here, it goes from 2 to 1 to 0 to negative 1 to negative 2. In other words, the gradient is always decreasing through 0. And you might be able to connect that to something that you've already learnt about the second derivative, the rate of change of the gradient. Okay, the rate of change of gradient is negative because it's decreasing all the time. So the gradient is decreasing, and therefore when the second derivative is negative, it's concave down. So we're thinking about down being the direction of the gradient, or the second derivative value is negative. If you think about the red part, the concave up, the opposite's happening. If you look at these, the tangents and the gradients of those, just to the right hand side of the point of inflection here, it's negative, a negative gradient, but of course it's flattening out to a turning point at the bottom, and then the gradient is becoming positive. So here's some snapshots of the gradient. We can see in that journey, negative 2, negative 1, 0, 1, 2, that the gradient is always increasing through 0. So the gradient's always increasing. In other words, the second derivative is positive. There's a positive rate of change of the gradient all the way through there. So what we really need to check for a point of inflection is whether the second derivative is a negative value, which means the gradients are going down, or whether the second derivative is positive, in which case the gradients are going up. And if there's a change from that point, the second derivative point, from negative to positive, then we can say we have a change in concavity. Okay, so let's have a look at how that might work in practice. So here's an example. Show if there is a point of inflection for the functions f of x equals x to the power 4 and f of x equals x to the power 5. So let's take the a first of all. So if we're saying f of x is equal to x to the power 4, we want to have a look at the second derivative. So we'll go through finding the first derivative, which is 4x cubed. And then the second derivative will be 12x squared. Okay, that's not too difficult there. So what we're saying here is that there's our point of inflection, possible point of inflection when the second derivative is 0. In other words, that's our change, possible change in concavity has to happen because the transition from negative to positive in the second derivative has to go through 0. So what we want to do is actually what we're saying here at this point, if there is a point of inflection, the second derivative is 0. Okay, I mentioned that, but I just wanted to make it a bit more explicit. Okay, so what are we saying here? We want to say that there's a possible point. Now I tend to write possible point of inflection. And I still use x, even though you could use c. When f double dash or f double prime x equals 0. So again, it's our statement of fact. We're looking to investigate this point here. We've worked out that it's 12x squared is therefore equal to 0, and we're saying divide both sides by 12 and take the square root. In this case here, we're suggesting that happens when x equals 0. So it's a possible point of inflection because it could actually be, in this case, a turning point. So let's check the concavity. And this, rather than check the nature, I want you to write check concavity, because that reminds us that we need to have a change from positive to negative, or up to down, in order for it to be true. So let's have a wee look at that, see if we can extend the page down. So we're going to draw a table, a wee nature table, just like you've done before for turning points. So we'll have 3 columns on the right hand side. So we'll have what we have. We've got, just like we did with finding turning points, we've got our value here. X is 0, so we're saying that the value that gives us a second derivative of 0 goes in here, and this is going to be a value slightly to the left of 0. So it might be -1 or 1 would do for one of these things. You'll have hopefully a bit of experience about finding nature tables for turning points. And what we want to examine here is what's the second derivative for these values, and we want to also write concave on the left hand side. Okay, so we've got 3 columns to investigate. We'll have a look at what happens in the middle first, because that's the one that's kind of predictable. So at 0, when x equals 0, remember, we know the second derivative is 0, which means that there is no concave. We can't say it's concave up or down. If you think about x being -1, I should maybe just put my x value there. Okay. When x is -1, well, remember we're looking at the idea of being second derivative. We're saying is 12x squared. Okay, so when x is -1, x squared is +1, and therefore times 12 is +12. In other words, we're saying that it's a positive value. If the second derivative is positive, then we've got concave up. Remember, second derivative is positive, concave up. Second derivative is positive. It means that the gradient is moving upwards. Okay. Let's have a look at the second column, or the third column. We're thinking up to the right hand side of our point of inflection, so a number bigger than 0, which will make positive 1. So in this case here, x squared, positive 1 squared is 1, multiplied by 12 is positive 12. So we've also got a positive value for the second derivative at 1, which means it also is concave up. Okay, so in other words, we're saying there's no change in concavity, so we don't actually have a point of inflection. So we would just say no change in concavity, so no point of inflection. Oops. Oh, I see, I used a C there. Point of inflection at x equals 0. Now, of course, the very astute among you will recognise the fact that x to the power 4 as a function, we actually know what that kind of looks like. X to the power 4 is just a kind of squeezed version of x squared. Get my wee pen here. So x to the power 4 still looks like a parabola. It's got steeper sides to it, but we know that at x equals 0 there's actually a turning point. It's not a point of inflection. Therefore we kind of anticipated that would be true. Okay, well, I did anyway. So let's have a look at the second one. I've got it down the right hand side here. X to the power 5. You might already know how that curve looks like. So let's have a look at this one here. We'll change the colour of it. We'll put it in black. So if f of x is x to the 5, then the first derivative is 5x to the 4. And the second derivative is going to be 20x cubed. We can say that there's a possible point of inflection when the second derivative is equal to 0. So what is our second derivative? Is 20x cubed. So we can say 20x cubed is equal to 0. Now that's going to, of course, result in the same answer as in part A. That here we're saying that x equals 0 is a possible point of inflection. So let's check for concavity. We draw a wee table. I'll draw it in 1, 2. Oh, they're a wee bit squint, aren't they? 3. That won't do. So what we're going to do, fill out our table. On the left hand side we'll put x and we'll put the second derivative. If it helps to write that in, then do so, just as a wee reminder. That's 20x cubed. And we also want to say a wee label on the left hand side, concavity. A bit like you would do with a nature table. You'd write the slope or the kind of shape of the gradient on the left hand side. So the three columns we're going to fill out. The middle column is going to be our value when the second derivative is 0, which happens to be 0. And again, we're going to investigate just to the left of that and just to the right. And you might want to write in possible points that you're going to use there, values for x. So we know that in the middle, when x equals 0, the second derivative is 0, and so that's fine. But for negative 1 this time, because it's x cubed, negative 1 cubed is negative 1 times 20 is negative 20, so we've got a negative second derivative, which means it's concave down. And when x is positive 1, x cubed is positive 1 times 20 means we've got positive 20 as our value. I'm not interested in your numerical value, just in the sign, which means that that's concave up. Which means that my analysis is that there is a change in concavity across the point. This when the second derivative is 0, it's going from concave down to concave up. So therefore we can say that there is a change in concavity. Change in concavity from down to up. Therefore, there's a point of inflection. Point of inflection at x equals 0, or if you went on, of course, you could find out the actual full coordinate point if you were required to. All you need to do then, of course, is take your value of x, put it into the original function, which was x to the power 5, which in this case, of course, is going to be at the origin anyway. So that's a kind of basic rundown of point of inflection. In example 9, I've got a different a function where the answer is not always x equals 0, but I wanted to show you the kind of structure of how we would examine for a point of inflection, and I hope that's been helpful.